Hello, and welcome back to Nightlamp Curiosity. I'm Professor Photon, and tonight we're going to take a quiet journey beneath the surface of everyday reality. Not into fantasy, not into speculation, but into the real, tested, experimentally confirmed world that exists underneath everything solid, familiar, and comfortable. What you're about to hear isn't strange because scientists exaggerate it. It's strange because the universe truly behaves this way, and because once you understand how the quantum world works, the ordinary world never quite looks the same again. Let's begin gently at the place where solidity itself is born. Everything around you feels solid. The floor beneath your feet, the phone in your hand, even the water. But that sense of solidity is actually an illusion created by forces, not by tightly packed matter. If you could zoom in far enough past skin and bone, past cells and molecules, you would reach atoms and you'd discover something quietly astonishing. Atoms are almost entirely empty space. Their mass is concentrated in a tiny nucleus at the center, while electrons exist far away, not as neat little dots, but as fuzzy regions where they are likely to appear. If an atom were the size of a cathedral, its nucleus would be a grain of dust floating at the center, and the electrons would be vague, cloud-like presences near the outer walls. So why doesn't your hand pass through the table? Because when atoms approach each other, their electrons repel one another through electromagnetic force. What you feel as solid is not matter touching matter. It's force pushing back against force. Solidity is resistance, not contact. That alone is one of the first quiet revelations of physics. The world holds together not because things touch, but because invisible interactions refuse to let them overlap. At the heart of each atom sits the nucleus, made of protons and neutrons. For a long time, these were thought to be fundamental, the smallest pieces of matter. But they aren't. Protons and neutrons themselves are built from even smaller entities called quarks. There are 6 known types of quarks: up, down, strange, charm, top, and bottom. And different combinations of just these 6 form every proton and neutron in the universe. It's remarkable to pause here and take that in. Everything solid you've ever known, mountains, oceans, cities, your own body, is built from fewer than 100 types of atoms, which themselves are built from just a handful of particles. Nature is extravagant in outcome, but economical in ingredients. Quarks are held together by one of the strongest forces known, the strong nuclear force. This force is so powerful that it overcomes the natural repulsion between positively charged particles inside the nucleus. Without it, atomic nuclei would tear themselves apart instantly, and matter would never have formed. The strong force is short-ranged but incredibly intense, like an unbreakable glue that works only at the smallest distances. Electrons, on the other hand, are fundamental particles. As far as we know, they have no internal structure. They are not made of smaller pieces. Every electron in the universe is identical to every other one. There is no way to label them, no way to tell them apart. An electron in your body is indistinguishable from one in a distant galaxy. This perfect sameness is not a limitation of our instruments. It is a fundamental feature of reality. And already the quantum world begins to feel different from our everyday intuition. In the quantum realm, particles don't behave like tiny billiard balls following precise paths. Instead, they are described by something called a wave function. The wave function doesn't tell us where a particle is. It tells us where the particle could be and how likely each possibility is. Reality at this scale is written in probabilities rather than certainties. This leads us to one of the most famous and unsettling ideas in quantum physics: superposition. A particle can exist in multiple possible states at the same time. An electron can be here and there simultaneously. Not because it's moving quickly between positions, but because until it interacts with something, its state genuinely includes multiple possibilities at once. This isn't philosophical speculation. It has been tested repeatedly in laboratories around the world. In the double-slit experiment, scientists fire electrons one at a time toward a screen with two narrow openings. Even when electrons are sent individually, they create an interference pattern, a wave-like distribution, on the detector behind the slits. Each electron behaves as if it passes through both slits at once and interferes with itself. Only when detectors are placed to observe which slit the electron goes through does the interference pattern disappear, and the electrons behave like particles again. Simply put, when you don't look, the electron behaves like a wave of possibilities. When you do look, it behaves like a particle with a definite position. This brings us to wave function collapse. Before measurement, a particle exists in a superposition of possibilities. When an interaction occurs, a measurement, a detection, a collision, and that cloud of possibilities collapses into one actual outcome. The theory tells us how to calculate probabilities, but it doesn't explain why this collapse happens the way it does. This is known as the measurement problem, and it remains one of the deepest open questions in physics. Closely related to this is the uncertainty principle. At the quantum level, there is a fundamental limit to what can be known simultaneously. You cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you measure one, the more uncertain the other becomes. This is not due to flawed instruments or human clumsiness. It is built into the structure of reality itself. Another counterintuitive idea is quantization. In the everyday world, things change smoothly. You can turn a dial gradually or pour water continuously. In the quantum world, many properties change in discrete steps. Energy comes in tiny packets called quanta. Electrons in atoms can only occupy specific energy levels. They don't slide between them. They jump. When they jump, they emit or absorb light. Every colour emitted by an atom corresponds to one of these precise jumps, creating a unique spectral fingerprint that allows scientists to identify elements across the universe. Then there is quantum tunnelling, a phenomenon that sounds impossible from a classical perspective. Quantum particles can pass through barriers they do not have enough energy to cross. It's as if a ball appeared on the other side of a hill without rolling over it. This effect is not rare or exotic. It powers the nuclear reactions in the sun, allows certain chemical reactions to occur in your body, and makes modern electronics like flash memory possible. Perhaps the most unsettling phenomenon of all is entanglement. When two particles interact in certain ways, they can become linked so deeply that they no longer behave as independent objects. Measure one and the other responds instantly, no matter how far apart they are. This connection does not transmit information faster than light, but it defies any classical explanation based on local causes. Einstein famously called this spooky action at a distance. He suspected that quantum theory must be incomplete. But decades later, experiments based on Bell's theorem showed that no local hidden explanation could reproduce the observed results. The universe truly behaves this way. Entanglement is real, measurable, and now routinely created in laboratories. Despite all this strangeness, quantum physics is not chaotic or vague. It is the most precise theory ever developed. Its predictions match experiments to extraordinary accuracy. Quantum electrodynamics, the theory describing how light and matter interact, predicts values that have been confirmed to more than 10 decimal places. The weirdness is not a failure of the theory, it's a failure of our everyday intuition. You might wonder why we don't see superpositions and interference in daily life. The answer lies in decoherence. Quantum systems are extremely sensitive to their surroundings. When they interact with the environment, air molecules, heat, light, their quantum behavior rapidly disappears. The system becomes classical. This is why cats, tables, and planets don't exist in visible superpositions. The quantum world fades smoothly into the classical world as systems grow larger and more interconnected. Underneath all particles lie quantum fields. Modern physics describes reality not as a collection of tiny objects, but as a set of fields filling all of space. Electrons are excitations of the electron field. Photons are ripples in the electromagnetic field. Even empty space is filled with these fields quietly fluctuating. The vacuum, therefore, is not nothing. Even in empty space, particles briefly appear and disappear, borrowing energy from the vacuum in accordance with quantum rules. These vacuum fluctuations have real effects, such as the Casimir effect, where two uncharged metal plates attract each other simply because of how quantum fields behave between them. Mass itself arises from interaction with a field, the Higgs field. As particles move through this field, they acquire mass, like swimmers moving through water. Without the Higgs field, particles would move at the speed of light, and matter would never clump together to form atoms, stars, or people. All of this might sound abstract, but quantum physics quietly shapes your everyday life. Chemistry works because electrons obey quantum rules. Your phone functions because semiconductors rely on quantum tunneling and energy bands. The sun shines because quantum processes allow nuclear fusion to occur. Even life itself appears to exploit quantum effects, from photosynthesis in plants to navigation in certain animals. And perhaps the most humbling realization is this: quantum physics does not describe a cold, mechanical universe. It describes a world where possibility comes first, where outcomes emerge from probability, and where reality is not fully determined until interaction occurs. At its deepest level, the universe is not built from solid things, but from relationships, interactions, and chances, constrained by precise rules. And from that subtle, restless foundation, everything you know and everything you are quietly arises. Thank you for staying till the end, and good night.